Okay. All right, what's next? I can't remember. What's the next one? Square root function. I think you're familiar with this one. At least different kids have mentioned it, so I think you kind of know what the square root function looks like. Its equation is y equal the square root of x. And again, we're going to modify that. We're going to put plus 2 in it. We're going to put times negative 3 in it. We're all kinds of weird stuff. But the shape will always be the shape. And the shape is this. Which you'll notice is the top half of a parabola opening to the right. Because a parabola opening to the right has this equation. And if you square root both sides, you get that equation, right? So that's that. All right, what is my domain? What x is it? 0 to infinity. We can take the square root of 0, so we're going to include 0, but we're going all the way to infinity. How about my range?
Oh, 0.
Yeah, we don't go negative, right? So it is also this. And the reason that we don't consider the whole parabola is because these are called the basic family of functions, right? That's not a function. So I can only look at the top half, now it's a function. And therefore, it doesn't be negative y's. All right, and behavior. What do you think? Yeah, isn't that shooting up? Now it's shooting out faster than it's shooting up, but it's still rising. There's no asymptote or anything, so yeah, that's positive infinity. What about the left?
Would it be no solution?
Does not exist. You are looking for a limit as x goes to the left. X can't go to the left, so therefore you have no limit. Now, there is a lower bound. This picture doesn't go below 0, but that is not its end behavior. It doesn't have anything going that direction. Okay? Now we have the exponential. Anybody know what E is? It does not stand for exponential. Anybody remember what E is?
Euler's number?
What?
Euler's number or something?
It's actually called Euler. It's pronounced
yeah.
Euler. But yes, E starts with an E. E-U-L-E-R. So that's, yes, it's named for him. What else do you know about
It's
it?
like
2.7.
2.718, yeah. What else do you know about it?
We use it a lot with L and N.
Yeah, well, you used it with ln because it actually is the base of the natural logarithm. So in a minute, we're going to do the logarithmic function. But when you have a log, that means nothing unless you have a base on it. And the common base that we use is base 10, because our number system is base 10. So when you press the LOG button on your calculator, it's giving you base 10. But if you press the ln button on your calculator, it is giving you base E. The base E logarithms, that's where you use it a lot. And then you have that growth formula. Do you remember? I don't know what letters you use, but I always call it the PERT formula. Did you use a formula kind of like that when you were finding interest or something last year? That's E right there. That's Euler's constant right there. Anyway, what I was saying before I love Euler's number, before I got sidetracked here, this is the shape of every exponential. So I have E here, because that's how we normally talk about it in terms of the basic function. That could be a 2, that could be a 6, that could be a 1/2, that could be anything, and the basic shape is gonna be the same. Okay, flipped around, upside down, stretched, whatever, but the basic shape is this. And here's what that basic shape is. Label that point 0, 1 right here, very, very important, because what happens when you raise any base to the 0 power? You get 1. That's why that point is there. It has a horizontal asymptote at y equals 0. Can someone explain that to me? Why is there a horizontal asymptote? Why doesn't this thing, like, keep going down or something?
So even if it's at the 0 power, it's 1.
So,
The negative powers don't go to 0.
so remember, if you are raising a positive number to a power, it's going to be positive, right? Think about that. If you take 4 to the 1/2, you get 2. If you take 4 to the negative 1/2, you get 1/2. The answer is always positive. So you're not gonna have any negatives down here. Domain. What's the domain of this function? X. Think about X.
Infinity, negative.
X can be anything. You have any exponent you want. But what's your range?
0 to infinity.
0 to infinity, and 0 is not included because it is an asymptote. All right, how about in behavior? What happens to the right?
Infinity.
Goes to infinity. What happens to the left?
0 on the top side.
0 from the top side, yep, from the top side, I like that, from the top side, yep, just like that. That's your exponential. All right, what's next? The natural logarithm function. Now, remember, this is a sheet of the basic functions. They don't have to be natural logarithms, they could be any logarithm, the shape will be the same. So what does a logarithmic function look like? Y equal ln x. But truly, this is for any logarithm, no matter what the base. What does it look like? Well, it contains the point 1, 0. We can spend some time talking about logarithms, but for now, you may already know this. Logarithms and exponentials are inverses of each other. These guys are inverses. And so if in the exponential, if plugging in 0 produces 1, then in the inverse, plugging in 1 will produce 0. We'll spend more time talking about that. You don't necessarily need to know that right now, but that is the case. They are inverses of each other. So if the exponential has an asymptote at y equals 0, the logarithm is going to have an exponent, or excuse me, an asymptote at x equals 0. And it's going to look like this.
That worked in the hundred house.
Every logarithm is going to have some variation of that shape. You can flip them, you can move them, you can stretch them, shrink them, whatever, but that's the shape. What's the domain?
0 to
Not including 0, right?
correct.
And what's the range?
Infinity, negative infinity.
Yep. Notice, remember, these guys are inverses. So notice what happens. This was X, and this was Y. What happened for the inverse? They simply flip-flop, which is what inverses do. They flip-flop. Okay, so let's talk about our end behavior. Our end behavior is going to be what? What happens as we go to the right? We're going up. There's no lid on this. It keeps rising forever and ever, just like the square root function does. How about to the left? What's my, doesn't exist. DNA does not exist. The limit does not exist.
Is that what we're gonna put on quizzes and tests?
Yep. Yep. Speak like calculus students.
Wouldn't it be like 0 plus though? Because it's an asymptote.
Okay, now remember, oh, this is the key right here. Where is x approaching negative infinity?
Oh, on the left.
They're out here, and I don't have a picture out there. Now, this is a little bit beyond our scope right now, but if I said what's the limit as x approaches 0 from the positive side,
That'd be 0 plus.
that would be negative infinity.
Oh.
These are x's. The limit is a y value.
Mhm.
These y's are not getting closer to 0. These y's are going
Down.
down to infinity.
Okay.
So if I did this, which is not in behavior, this is not in behavior. But if I did the limit as x approaches 0, that means x is getting closer to 0 from the right side. Then I can say y is negative infinity.
Okay.
But that is not in behavior. I'm glad you asked that question. That's a big point to make sure you're clear on. This right here in the notation itself, those are your x's. The question is, what's happening to y? Okay, what's happening to y? All right, now we've got our trig functions. And we're gonna spend some time graphing our trig functions. Don't fear, you're going to graph a lot of trig functions. But what are the basic shapes? So your sine function, the abbreviation is SIN. SINE is the name of the function. It's abbreviated SIN. So if you look at your calculator, you have an SIN button, right? Never say sin, that makes you sound goofy, right? It's sine X. The sine curve, now I don't know, this grid is kind of small, but somehow indicate that it's going to go up and down 1 unit. So you can change your scale or try to get it in one block, it's gonna be really small. The sine curve, right here, put it out there, the origin. The sine curve contains the origin. And there's a little hill going up 1, and a little valley going down 1. And then it just keeps going. So we have it in both directions. And it just keeps going forever and ever. We'll worry about the horizontal labels later. So I don't want you to get all hung up about it. I'm not sure how much you know about radian measures, and that's how we would label this. So that's the general shape. Right now we're focusing on the general shape. What is our domain?
Infinity,
Yep, everything. You can take the sign of anything you want. Someday when you're bored, not in this class obviously, but in some other class, take out your calculator and start taking the sign of things. You can put anything you want. Decimals, fractions, doesn't matter. Positive, negative, doesn't matter. But what's your range? So -1 to 1. That's your range. This is our first, what we call bounded function. Bounded function. Bounded means that there's a ceiling and there's a floor. trapped in between. Now think about your exponential. The exponential is not bounded. It has a lower bound, right? It has a floor, but it does not have a ceiling. When someone says to you this function is bounded, that means it has both a bottom and a top. So this is our first one. Okay? Sine and cosines have no end behavior. Well, we haven't done a cosine yet, but sine functions have no end behavior. Why? What happens?
They just keep
As
on
I keep going, I walk across the hall, what is my sine curve doing? Going up and down, up and down, up and down. It's not approaching anything. So DNE, no end behavior for sines and cosines. They're oscillating. We haven't done cosine yet, but it's going to look just like this. Up and down, up and down, up and down. So what does a cosine look like?
Same as that, but it starts at 1.
Exactly. Oh, wowzy. That's awesome. Cosine X. Still up 1 and down 1. It's the same basic curve. But instead of going through the origin, it intersects the y-axis at 1. So it's still got the same hills and valleys, but it looks like this.
This is about the last one, but like, there's no asymptotes in that.
No asymptotes in that. No. What, let's back up. When do vertical asymptotes happen? When there's something that X cannot be. X can be anything. There's no horizontal asymptotes because there's definitely a ceiling and a floor. But those aren't asymptotes because when you have an asymptote, you approach it. That's what an asymptote means. The farther you go, the closer you get. That's not what's happening here. It's like going up and bumping and coming back down. No asymptotes. The sine and cosine. Okay, how about domain and range for this guy?
Negative infinity to infinity.
Same, right? Same domain and range. And still no end behavior. Now, apparently you guys already know how to tell sines from cosines because somebody told me. Here's how I remember it, because I'm gonna have to graph, you know, weird, crazy things like, you know, that, we're gonna be graphing things like that, and I need to know how to start my picture. So I remember, I know it's dumb, but I'm an old Catholic girl. I remember the idea of original sin from my religion classes. And what does that remind me?
Origin.
That the sign goes through the
Origin.
origin. That's how I remember. I don't care how you remember, but remember, because you gotta be able to draw your sines and cosines accurately. All right, what's next? Aren't you just excited about graphing something?
So excited.
Yep. Next we have the absolute value function, which I know you've spent a lot of time with this because it's in the Algebra 2 curriculum big time. What shape is it? It's a V. Absolute value V. It has exactly the same characteristics as the squaring function, because the squaring function is a U and this is a V, but they have the same domain and range and the same end behavior. So your domain is all real numbers. Your range is 0 to infinity, so the positives. Because when you take the absolute value of something, it's positive. And then your end behavior, up. but up, I'm up on both sides. So positive. Now, my totally least favorite, and honestly, it's not part of our curriculum, and we never do anything with it, it's general knowledge. So the greatest integer function, we're not gonna spend any time with, but we gotta get it in our BFF list. The greatest integer function. We'll move it out of the origin. And however you're gonna scale your paper, because I know those blocks are very small. But draw a bar over 1 unit and put an open circle. So you have a solid dot at the origin. Go 1 unit over, color that in, that's part of the graph right there. And then put an open dot. Then step up 1 unit and put a solid dot. Right above that open dot, put a solid dot, and then repeat. So over 1, open dot. Up 1, close dot, open dot. So this is easier for me because I don't have the grid like you have, but these are 1 across, and these are 1 up. So we're stair stepping. And the same thing down here. It would look like this. I like you to start with the origin now because the origin is gonna be closed. So that kind of gets you started. They're not connected. This is sometimes called a step function. A step function. I don't like them. I don't like them because all the characteristics here that we talk about are totally weird for this function. But this is part of life. When you, I don't know if you guys ever like actually mail letters anymore, you like a letter with a stamp and mail it. But if your letter weighs up to an ounce, you have to put 1 stamp on it, right? But if it weighs more than an ounce, you have to put 2 stamps on it. And that is, it can weigh 1.1, 1.2, 1.3. All of those put you up at the 2-step mark, or the 2-stamp mark. That's what this does. Everything, all the x's in this interval are y0. But as soon as you get here, then it skips up, and now the y's are 1. And then as soon as you get here, you skip up, and now the y's are 2, and so on. All right, now what's your domain? Everything. Right? Your x's are everything. Isn't every x covered there? Yeah. It keeps going. What's your range? This is where the weirdness starts. What's your range? Just the integers. Because these have a y value, all these y's, if you plotted all these points, they would all have a y of 0. And then these would all have a y of 1 and 2 and -1 and -2 and so on.
So like if the steps are like up by like half or
No,
something.
they're up 1, this is 1, this is 1.
I know, but like what if like the whole thing's like raised up by like half or something?
Mhm.
We do like integers plus 0.5 or something like for
You would
range.
have to, but remember, we have all kinds of modifications that are gonna change lots of things. We're looking at just the basic functions now.
Do those brackets have any other use in math? Or like the y equals the x in brackets?
Up here,
Yeah, like do we use those in anything else for math besides like interval notation?
not that I know of, this is greatest integer notation. Now, on your calculator, you can graph these on your calculator, but you'll graph them like this, and the int, that is your greatest integer notation. Sometimes I've seen it like this, kind of like mixing the bracket and the absolute value. Sometimes it looks like that. But remember, it's just a formality. It's to say we did it. All right, and then the last one, oh wait, end behavior. What is the end behavior for this guy, the greatest integer function? What happens to my y's? What happens to my y values as x gets bigger? They get bigger. And what happens to my y values as x gets smaller?
They get smaller.
They get smaller. This is our logistic function, called the logistic function. It has many uses in math, and we will run into it, but it isn't gonna be a point of emphasis. Our points of emphasis are really going to be the first, basically 10 of these. They're gonna be all good parts of us. What does this look like? Well, again, watch your scale here. You're gonna have an asymptote at 0, a horizontal asymptote at y equals 0. And you're gonna have a horizontal asymptote at y equals 1. Now, I want you to think about that for a second. So this is up 1, so skip some spaces. That's up 1. I want you to think about this for a second. If I look at this equation, that would really be this, right? And E is 2.7. I'm just gonna say 2 in front of it. I want you to think about what happens as x gets really, really big. As x gets really, really big, then doesn't 2 to the x get really, really big? But what about 1 over 2 to the x? It gets really small. And in fact, it gets so small that pretty much it goes away. So we have basically 1. So as x gets really, really big, we're going to be approaching 1. Now, think about this. What happens as x gets really, really small? Well, as x gets really, really small, go back to the original. What happens if x is negative? If x is negative, then this becomes e to the x, right? And e to the x, 2 to the x, gets bigger and bigger and bigger. So 1 plus that gets really, really big. So now my denominator is really, really big. So what happens when I put 1 over really, really big? I get closer to 0. So on this side of the curve, I'm limited by 0, and on this side of the curve, I'm limited by 1. That is what your logistic curve looks like. What is your domain? Negative infinity to positive infinity?
Yeah.
What is our range? 0 to 1. Now again, to Cole's point, we're going to start sticking numbers in there and things are going to shift around and move, but the fundamental, the basic range is 0 to 1. What's my end behavior? What happens as I go to the right? closer to 1 from the bottom. That does not mean negative 1. That means I am approaching 1, but I'm coming in from the bottom as opposed to coming in from the top. And what happens when I go the other way?
0.
Then I am approaching 0
From the top.
from the top. Okay? Now, we got all the curves. You are responsible for knowing all the stuff we talked about. Okay, so the name, the picture, the equation, the domain and range, and you don't have to memorize all this stuff. If you remember what the picture looks like, then you ought to be able to figure out domain, range, and the behavior, right? So really focus on remembering the picture. Now, I gave you today practice sheet. Let's get that out.
This is good.
Yeah,
I never got those
put
notes.
it right up here.
Alright. One of each. One of each, one of each. If you have it on there.
Okay, so one side is called transformation practice. Let's start with that, transformation practice. So we're gonna sketch y equals the absolute value of x plus 1. All right, so first of all, what shape is it?
V.
A V. What does tacking a 1 on the end of my problem do to the V? Moves it up 1. So now we're not at the origin. Now we're V'ing from that point. And that's all you have to do, kids. This is just a rough sketch. You're not plotting a bunch of points. It doesn't have to be perfect. I want to see a V with that point label right there. Now, what about 2? This is another, what we call translation. We're going to pick the picture up and move it. But first of all, this will be a parabola. And it's, how is it being moved? Right, 2, exactly. Right, 2. So a number outside of the function. So there's my function. A number outside of it moves you up and down. A number inside the function, see how the whole thing is getting squared, moves you left and right. And when it's inside, it's the opposite of what you might think. So x minus 2 is actually going to the right. X plus 2 would go to the left. All right, number 3. Now, you're brand new at this, right? I think anyway, pretty much brand new. So let's just refresh our memories here. What is the basic logarithm? A logarithm. What does the basic logarithm look like? Has an asymptote here at x equals 0, and it has an intercept here, and it does that. That's the normal. Now, what change is this doing? Left 1. Left 1. So that means your asymptote now won't be at 0, it will be at -1. And your intercept won't be at 1, it will be at 0. The shape will be exactly the same. You've just picked the picture up and shifted it 1 unit to the left. All right, we got 5 minutes. See how many more of these you can get going. Use your notes. Some of these are brand new shapes to you, so feel free to use your notes, your BFF sheet.
board.
Oh, no. I just looked at what I think are the easy ones. What about this guy? What is happening here? Pay attention. Oh, wait a minute, I wrote it wrong. Is that what I've got on paper? Yeah, okay, yeah, it makes a big difference. Okay, so what's happening here? Everything is coming down to 2. So the asymptote that was at y equals 0 is now gonna be at y equals -2. And the intercept was at 1 is now at -1. Does that look okay to you? I moved my parabola up 3. I moved my V left 4. Now, what shape is this? This is a cube. What shape is that? It's a squiggle. And the normal squiggle is at the origin. And when I say the squiggle, it's a change in concavity. This is concave down. This is concave up. Concave up means it holds water, concave down means it doesn't. So this part of the curve is down, this part of the curve is up. So now where will that point be? I am moving that point now over to here. So now my concave down to concave up switches at that point. Does that make sense to you? What happens here? Same thing, but now that point is up here. So I'm concave down till I get to there, and then I'm concave up after that. I don't know if you noticed, this is your line, right? Your line. And I don't know how you thought about it. Did you think about it moving it down 4? You can also think about it as moving right 4, because that could be in parentheses and not change anything. It's the same equation. Either way you go, it's the same line, right? For our next class, which is when? Tomorrow? No?
No.
Tuesday? I want you to do the other side. Give the other side a shot, okay? Give the other side a shot. This is an old quiz I gave many years ago. We're doing it as practice now. All right?
I just blind all the time.
What's the matter?
I was just drawing.
Okay, you can draw all you want, but